separation of variables. Example, two infinite grounded metal plates lie parallel to the xz plane, one at y equals 0 and one at y equals a. The left end at x equals 0 is closed off with an infinite strip and insulated from the two plates and maintained at a specific potential v0 of y. We find a potential inside the slot. Now the configuration is independent of z, so this is really a 2D problem. So we can use a Laplacian here. We call equation 1, subject to the boundary conditions here, where our potential is 0 when y equals 0, and so on and so on. The latter is necessary because further from the h d strip at x equals 0, the potential drops off to 0. So since the potential is determined on all boundaries, the answer is uniquely determined. The first step is to look at the solutions of the form here in our separation of variables form. So we call this equation 2. So putting 1 and 2 together, we'll get this here from our Laplacian. This is equation 1, equation 2. So we're basically plugging this into this and we'll get this. Now we divide through by our v, our potential, and we'll get this here. So now we have it in one side in terms of y and the other side in terms of x, and both equal 0. Now it is in the form of fx plus g of x equals 0. This is true if f and g are constant. So we can set each side of this to a constant c1 and c2, say, with c1 plus c2 equals 0. Now we'll set our x to our k squared of x and our y to a negative k squared of y, because this is the only way you balance the equation. Now we find a PDE. Now we've obtained a PDE, turned a PDE into an ODE, which we can solve. Now our standard solutions of x equals this and y equals this, because of our negative k in this case. So our potential v of x of y is given by here. So this condition requires a to be 0. Absorbing b and c and d, will get this. D equals 0 by I, by our I condition. Where did I put that? It's up here somewhere. Oh yeah, by this condition. So v, our potential v over x equals c e to the minus kx sine ky 3. Now this I've called equation 3. It's not part of that. And this are our conditions, our second boundary conditions. Here y v of 0 equals v equals 0 when y equals a. So by our second boundary conditions, which yields a sine of ka equals 0, so k equals n pi over a, where n equals 1, 2, 3, and so on. Now c1 was chosen to be positive, c2 negative. If x were sinusoidal and could not get 0 at infinity, and if y were exponential, we could not make it vanish at 0, and a, also n equals 0, is no good because potential would vanish everywhere. Now using separable solutions, and unless v0 of y just happen to be this same form as sine n pi y over a for some integer n, we can't fit boundary conditions at x equals 0, but the crucial step, separation of variables, has given us is an infinite number of solutions, one for each n. And whereas none of them by itself satisfies the boundary condition, it is possible to combine them all in such a way that it does. Laplace is linear. in the sense that v1, v2 and so on satisfy it. And so does my linear combination of row. V equals alpha 1 v1 plus alpha 2 v2, so on and so on, where the alphas are arbitrary constant. Now for del squared of this, we're simply squaring these terms and so on, which again equals 0. So by using 3 to construct a more general solution, we'll get here this as a solution. Thus, this satisfies the boundary conditions, and we can choose a C of n to fit boundary Can we choose C of n to fit the boundary conditions? These boundary conditions. Again, these boundary conditions. V equals some v naught of y when x equals 0. Now, for equation 4, v naught of y from our boundary conditions, and we must make it equal this by what I've just saying, by these boundary conditions. This is a Fourier sine series, and Dirichlet's theorem guarantees that any function v naught of y, that it can even have a finite number of discontinuities, can be expanded into such a series. Now we use Fourier's trick to find C of n. We multiply equation 4 by sine of n prime pi y over a, where n prime is a positive integer, and we integrate from 0 to a. So we'll get this. And the integral on the left is this, now, which has solutions here. So our C of n is this. Now we suppose a strip at x equals 0 is a metal plate of constant potential v of naught. Remember, it's insulated from grounded plate y equals 0 and y equals a. Then our C of n is thus given here. And this is when n is odd and 0 when n is even. Now then, v of x of y equals this here, which is equation 5. Now v over v naught, about 1 here. The plot of potential shows the first few terms in our Fourier series combine to make better and better approximations of v of naught. The infinite series in equation 5 can be summed explicitly, and the result is thus here, which satisfies all of the boundary conditions. So yeah, and our boundary conditions are here. You want to make a note of these. So that's separation of variables in the electromagnetism context. Please do like and subscribe. There's lots more to come.